This is Project 5, our final term project by Team 561-1. Now I will pass it to Abbie to go over our introduction.
Thank you, Anna. So Project 5 is a culmination of all the knowledge and insight gained in the previous projects. You're able to see how every assignment within the course worked towards our final task of autonomously drawing a designated drawing using an ABB robot. With Project 5, we wrote code to program the ABB robot to draw the Flash logo. Our program had two key components, the circle and lightning bolt. We then simulated this code within RobotStudio to ensure the program works before in-person testing. For the testing portion of this project, we ran our program on the ABB robot and worked with Miguel to debug errors we encountered before finally getting our code to run successfully. Now I will talk about the agenda for our presentation today. So today, we will start by reflecting on our final schedule we followed and executing the main deliverables of the course. We will then use various visuals to review the main concepts and takeaways from previous projects that led to the successful completion of Project 5. These projects include Project 2, which was the 3D design of our pen holder, Project 3, which describes our toolpath for printing, and Project 4, which was the physical 3D printing process of our pen holder. We will then transition into discussing Project 5 and how it was completed through our final lab session. We will then reflect on what we learned from this final lab session and difficulties encountered. Finally, we will discuss the social implications of robots within our industry and discuss our study of it. We will conclude with remarks on all that we've learned throughout the semester in industrial robotic programming and why this is important moving forward. I will now pass it over to Anna, who will discuss our Gantt chart used throughout the year.
Thank you, Abbie. This is our team's updated Gantt chart. A Gantt chart illustrates a group or organization's project schedule, including their milestones and progress. Our milestones are represented by triangles and depict major goals for our team. The completed tasks are illustrated by solid rectangles and show our progress throughout the semester. The bolded rectangles with no fill represent our predicted completion dates. As you can see from the chart, we have almost completed all of our goals and milestones. Once we complete this presentation and Project 5 report, everything on the schedule will be done and our team project will be completed. Now I will pass it to Ryan to go over our project summaries.
Thank you, Anna. So this next portion of the presentation will be going over our last few projects that have led to Project 5 and what made it successful. So first off, we had to design our pen holder. So as you can see in each of the images, it was completed with a few different main components. So we designed it in SolidWorks, and on the left, you can see the spring design. You can see it in both images. And then you can also see our attachment fixture hole. So this went through so that the attachment arm would be able to connect on several points so that it didn't wobble. And you can actually see the attachment fixture it's a little translucent here, but it threads right through. Next, we have the pen hole that goes through the base of the design. And you can see the pen going through it right now that would hold it in place. And finally, very important, the set screw holes. So we had one for the pen and for the attachment fixture to make sure that they didn't just slide out and they would be able to be secured. And next was Project 3, creating the toolpath for 3D printing. So you can see our model in the Cura software here, and you can also see on the right what each of the colors mean. So the most important color to look for is the blue, which are the support structures. So one of the most important things when creating this was to try and limit the support structures as much as possible, but have them where they're needed. So the main place that they're needed is for the spring, but also for the holes to make sure it doesn't sink through. So one of the main things that we did when designing the toolpath was ensure that these two holes that you can see in red, we made sure that those were on top, because if they were oriented on the bottom, there would need to be more support structures through them holding them up, which would be more filament and be difficult to remove and could cause other issues. So here we needed to limit our support structures and limit the amount of time that it took. So it takes a very long time to 3D print. So even after limiting these features, it still took about 3.5 hours, a little over. So we needed to make sure that the layer thickness was as small as we could make it, or else it would take upwards of 7 hours, which we just did not have. And another feature when setting up the toolpath was the infill density. That also contributes to the time, but a little bit less. We just needed to make sure that it was filled enough to support each layer, but it didn't need to be completely filled, or else it might be too heavy, which could cause other problems. So now I'll pass it to Abbie so she can talk about the actual 3D printing process in the lab.
Thank you, Ryan. In Project 4, we 3D printed our pen holder. It took 2 trials to get our final pen holder design. The runtime for each individual trial was about 3 hours and 30 minutes. Throughout the printing process, we would check on the prints incrementally to make sure that the pen holder looked as we envisioned it. During this process, we realized improvements needed to be made to the first design, so we stopped it after roughly 2 hours of printing. In total, it took us about 6 hours before we got our final pen holder design. After printing out the object, we then had to remove the support structures and excess filament using tools such as screwdrivers, pliers, and sanding paper. I will now pass it off to Ryan, who will begin the discussion on our final lab sessions.
So thank you, Abbie. So this section of the presentation will be going over what we did in the actual lab session. So it'll include the final assembly, attaching the pen holder to the robot, and the strategies going into the lab with the toolpath and calibration, and also going over some of the issues that we've encountered. So first, this is a final assembly of the robot. So as you can see in green, the attachment fixture connects to the robot, then the pen holder connects to the attachment fixture, and the pen is connected to the pen holder. So we attached the attachment fixture to the robot with M6 screws that screwed into the plate on the robot, and we connected the pen holder to the attachment fixture through a set screw as discussed earlier to keep it in place, and connected the pen in the same way. For this project, we actually ended up not needing the set screw for the pen because the friction was enough to keep it in place. So that worked out, but in most cases, you'll probably need a set screw to prevent it from slipping out. Some of the issues that we had with the pen holder, and connecting it to the robot, some of the things we need to fix were that the model had some excess filament in the holes and was rough throughout. So when printing it out, we needed to make sure we removed all of the support structures, which were preventing the attachment portions from going through. But we also had some rough edges on the inside and the outside that needed to be removed. So we utilized the tools in the lab, as Abbie said, to remove these main parts. And the next much bigger problem that we had in the lab was that there was filament between the spring and the base that needed to be removed. So as you can see, we had to actually break off the spring, then remove the filament, and then super glue it back together. Luckily, Miguel had super glue on hand, so we were able to do this, but it was not ideal. We perhaps could have avoided this by printing it differently, but we didn't have a ton of options, so this is the route we had to go by. And finally, another issue we had was that the dimensions were too small to fit the set screw. So obviously we needed the set screw to attach the pen holder to the robot. So we ended up needing to drill a hole through the actual pen holder so that the screw could fit because it was too small. So we did this right before the lab, and it ended up working very nicely. And now I'll pass it on to Caroline to go over our toolpath and calibration and some of the issues that we had with that.
Thanks, Ryan. Okay, so before the lab, we wanted to come up with a strategy for our toolpath and coding it. So we wrote our code for our logo on RobotStudio, and we didn't write the code for the full logo. We just wrote it for the lightning bolt because we were going to add the instructions for the semicircles during our lab period when we came in to execute our final design. And so we did this because we knew the lightning bolt would be relatively easy to code because we already knew how to program straight line images from the first lab with the block M. And we had not learned how to program circles yet, and Miguel recommended for us to do it on the lab day. And then once we got into the lab, we needed a strategy to calibrate the pen with the robot. So we needed to give the computer information to know where the position of the pen was at all times in relation to the robot and the whiteboard space. So first, we attached the pen holder to the robot. And second, we moved the calibration rod into our workspace right next to the whiteboard where the robot would execute our final design. And then finally, we moved the robot so that the pen is touching the calibration rod in 3 different positions and then a 4th position above the rod. So the pen touched from a left angled position, a right angled position, and then directly on top parallel to the rod. So then to get the robot ready to draw our design with the pen holder, we had to record a safety position about 6 inches above the whiteboard at an angled position, and then record a starting position on the whiteboard, which was our initial coordinate for the lightning bolt. So in the lab, we actually encountered a couple errors. So the first issue we encountered going into the lab was the calibration of the tool pin. And then the second was a slanted whiteboard. So these 2 problems affected how our design was drawn and increased the time that we had to spend in the lab to find solutions to these problems. The first time we calibrated our pen holder with the drawing surface and the robot resulted in a large mean error, which indicated that our calibration was not precise enough and would distort our final logo design. This error most likely came from accidentally touching the calibration needle too hard on the third point with our Sharpie, and therefore moving the needle very slightly, but enough to significantly mess up our calibration. To solve this, we recalibrated using more careful movements of the robot with jogging techniques, and our mean error was decreased from about 1.4 centimeters to 0.05 centimeters. So the second problem with our testing setup was the whiteboard, which is the area where the robot executes the toolpath. And this was due to another team and their choice of a slanted whiteboard for their project, but we didn't know about this until about halfway through the lab. As shown in the photo, the slanted whiteboard caused gaps in our design and uneven tracing of the two semicircles in the logo. So our solution was attempting to straighten the board, as well as modifying the points for the semicircles to adapt to this aspect and avoid the gaps. So the third issue we encountered during the testing of our toolpath in the lab was the shape of our design. So as shown by the red arrows in the photo, the circle around the lightning bolt proved to be one of our biggest challenges with our design. In the Flash logo, we were aiming to draw the circle around the lightning bolt is not complete, but rather two semicircles, and we really wanted to attempt to replicate this aspect. To have the robot draw the two semicircles with the Sharpie, we had to modify and store 3 key points. However, we discovered it was difficult to judge whether the points would be equivalent on each side, as we didn't use coordinates, but rather just movements of the robot to visually and mentally calculate where the points should be. This led to the issue of asymmetrical halves, and we had to use multiple attempts at modifying the points. Another issue that contributed to this was our miscalculation of how small our design would be. Our logo turned out to be only 2 inches wide, and this made it difficult to precisely plot the points for our semicircles based on just looking at the lightning bolt. So after multiple attempts of just trial and error for modifying the points, our team was able to produce a relatively symmetrical design. So now I'll pass it on to Ben, who would talk about our final drawing.
Thanks, Caroline. So for our final drawing, we were able to produce the Flash logo. We picked this design for a few reasons, one of which being that we all know the Flash and therefore related to what we were trying to create. And then another reason we like this design a lot is that we felt it was realistically within our capabilities as programmers, but it still presented a challenge with creating the 2 components. One of these was a circle, which was something we had not learned how to make yet. And this image to the right shows what our final drawing looked like once it was complete, as well as the coordinates we used for our code on the left side of the screen. I'll now pass it on to Anna for the video of our toolpath.
Thank you, Ben. Now we will show a video of the ABB robot drawing the Flash logo using our pen holder in a Sharpie. Next, I will talk about the improvements we can make on our project. While 3D printing our pen holder, our spring fell off and it had to be glued back on. In order to avoid this issue in the future, we could have changed the orientation of the spring in the CAD and 3D printing process. In the lab, we had issues while trying to set the points for the circle. We later realized this was because the workspace was calibrated at an angle. To fix this problem, we recalibrated with precise jogging movements. However, if we would have recalibrated the workspace to begin with, we would have saved a lot of time. A final improvement on our project would be to make our drawing of the Flash logo larger. When writing the code and coming up with the coordinates for our image, we made the scale way too small. In order to improve our final image, we can make the scale of our coordinates larger. And now I will pass it to Abbie to conclude this section of the presentation.
Thank you, Anna. All of our work throughout the semester has led to a successful and satisfying outcome of operating the ABB robot, such that it autonomously drew the Flash logo using a custom pen holder. All 5 projects throughout the semester have worked to develop our understanding within the fields of engineering, social science, and technical communication. Within engineering, we've learned about CAM, RobotStudio, and SolidWorks softwares, which we've used to design a pen holder and program the ABB robot. We also learned the basics of operating and calibrating the ABB robot and operating the Ultimaker to 3D print our pen holder design. We applied social science to our work with industrial robots as we analyzed their impact within manufacturing and reflected on how the workforce is affected by changes within the industry. Additionally, we learned about ways in which to conduct studies to further analyze robots' effects within different industries. Lastly, we developed knowledge and technical communications across the projects as we learned various types of mediums in which to communicate our results. These included memo reports, instructional reports, and description reports. Additionally, we developed the tools in which to create a detailed Gantt chart that we used throughout the semester to maintain pace with project deadlines. Throughout the semester, we've used all the knowledge we've gained in the past 5 projects to grow in these 3 fields. The projects have demonstrated the importance of industrial robotic programming and its impacts are related to additional industries. I will now pass it off to Caroline, who will further discuss the social implications of robots within the art industry.
So the largest social impact that our team focused on was the effects of mass production on art consumption. So the first advantage of mass-produced art we discussed was the ability of artists to share their work with a greater population, and in turn, this comes with wider accessibility for consumers. Although this may take away personal and monetary value from a piece of art, the wider availability would subsequently allow for greater affordability. So consumers who would not otherwise have the funds for typically expensive handmade art would now be able to purchase art created by robots due to this mass distribution and resulting lower prices. Because the use of robotic machines to manufacture art is increasing, this also allows for a growing community of new artists. Those who were unable to be an artist in the past due to disabilities, inexperience in handmade art, etc., now have the ability to create art by themselves and share their talents, while those who are able to create art by hand can opt to use robots for efficiency. As for the disadvantages of robotic painting used in manufacturing art, it has the potential to decrease the demand from consumers. As I said before, mass production may take away personal value, as a piece of hand-painted artwork is generally considered unique and consumers are attracted to this. So it may decrease demand if it loses this human aspect. Additionally, because of increased availability, there may be less demand for this art from consumers, which could negatively impact the production industry. So now I'll pass it on to Ben, who's going to talk about a theoretical study we could do on the societal impact of robotic painting.
Thanks, Caroline. So in order to better understand the societal impacts of robotic artwork, we decided to design a study based around how consumers of art felt about artwork made by robots. Although we wanted to be unbiased, random selection in this case was not the best approach, as it was more appropriate to reach out to people who are interested in art in some way. The question we're seeking to investigate is as follows. Would the fact that a piece of art is made by a robot negatively impact people's feelings about that said art? Our initial hypothesis was that if people know art is made by a robot, they'll find it less attractive or less valuable. Because artwork is based much around creativity and very open to discussion, we are targeting qualitative research with our research process involving a discussion with research participants about features of the art such as creativity, beauty, originality, and aesthetic before and after learning that the art was created by robots, as well as openly talking about their feelings towards the art. We're also going to make our research process longitudinal. We consider the option of cross-sectional, but to see how people's opinions would change over time, it would be troubling to gather information in a qualitative manner and would not really provide any additional insight into our specific question. Using a focus group will be the best option for our research, as we're looking to gauge how people feel about this issue, and one of the most insightful ways to determine that is through discussion. We are also going to consider demographic characteristics, such as age, gender, income status, and education level in our research, to see if there are any correlations in people's feelings about robotic art. The 2 questions we have designed to ask people for our research are as follows. Question 1, how do you feel about having robots painting instead of people affects the enjoyment of having the art? And question 2, do you think the sale of art created by robots is ethical, considering it will cause people to become less likely to pursue creating art as a career and cause many already practicing artists to lose their job? By asking research participants these questions, we hope to gather insight on how robotic art is affecting society, as well as what the best actions are to create a better society for everyone in the future. I'll now pass on to Anna for our conclusion about the societal impact.
Thank you, Ben. As our world becomes more digital and we become more dependent on robots, new technologies and robots such as self-driving cars become more incorporated in our everyday lives. Robots are constantly being used to complete tasks in the most efficient ways. They are constantly being expanded into new industries, as seen with robots in the medical field used in surgery and rovers within space exploration. In addition to technical knowledge, robotic programming develops skills utilized across industries as it engages problem solving and communication skills. This is one concept that our team found especially fascinating, as this course has demonstrated how engineering is connected with many other industries, demonstrating how it is important to not just learn and consider engineers individually, but its impact as a whole. The largest impression this class has made is in reiterating the moral responsibility of engineers, as products we design today can have far-reaching effects across many different industries in the future. Thank you.